Hi everyone, I'm Moses Sakashita, and today I'm going to present our work, RemoteCoDe, Robotic Embodiment for Enhancing Peripheral Awareness in Remote Collaboration Tasks. Collaborative design activities are often centered around physical artifacts, where they collaborate and discuss on their design task. These activities involve complex sets of configurations and tools. Despite the complexity, people can still easily understand each other and work together when they are co-located in the same space. This is because they can quickly gather information to be aware of what each other is doing in the workspace. Previous work on telepresence applications has explored ways to get people connected to collaborate across different locations. For example, video conferencing tools are often used for having meetings or editing digital documents, but they often fall short of supporting hands-on tasks where a physical artifact is involved. Telepresence robots have been explored to afford a strong sense of co-presence and being together. However, they often require users to use their laptop and keyboard and mouse to control the robot, and dividing their focus and attention between the robot control and the design task can be problematic and distracting their flow of collaboration. Some other work proposed automatic control for such robots so that collaborators can focus more on their collaboration. These systems are beneficial, but they are optimized for face-to-face conversations, and so they do not usually support multiple task areas that are necessary for collaborative design tasks. We developed a system called RemoteCoDe that allows collaborators to understand each other's locus of attention, providing peripheral awareness through the robotic proxy. RemoteCoDe was designed to support circuit debugging sessions where collaborators have to shift their focus between the breadboard, computer displays used for firmware programming or documentation, and of course their collaborators to work with. In these scenarios, collaborators have to rotate their head to switch locus of attention between these three different areas: circuit, monitor, and collaborator. Our RemoteCoDe has an automatic control mechanism so that users don't have to control using an interface, but instead they can use head rotation and focus on the primary design task. As you can see, as the remote person changes their focus by rotating their head direction, the robot's movements are reflected through the robotic proxy accordingly. To design such a system, the system must track large head movements to be able to look at different areas of interest around a desk, track and visualize facial expressions to convey emotional states and attention direction, and take different physical configurations and setups into account to accurately communicate each other's locus of attention. For tracking a wide range of head rotations around a desk, the system uses iPhone's TruthDepth camera. Our system can always display a front face of a remote user so that their partner can easily guess attention direction. To achieve this, we first obtain information about a user's face, such as mesh and texture, using iPhone's TruthDepth camera. Then construct a 3D model using this information, and finally pick a right angle of the 3D model to display a front shot of a user on the robot. In a circuit debugging session, they often set up their physical configurations differently. For example, Alice has her breadboard in front of her on the desk, but Bob has the breadboard on the monitor in his right side. Simply using Alice's head rotations for the robot control does not work because Bob can misinterpret the locus of attention that area Alice is looking at. To solve this, RemoteCoDe includes a remapping feature where the system remaps users' head rotations to the movements of the robot, so that both movements are consistent across the two different locations. Here's the demo of the remapping feature. You can see that the area the user is looking at is reflected through the robot on the other side as well. Right now, both of the user and the robot is looking at the firmware programming. We conducted user study to evaluate the RemoteCoDe system. The primary objective of the study was to investigate whether the system can support peripheral awareness for users. We recruited 13 participants and asked them to complete 2 different tasks. Today, I'd like to focus on one of the tasks on attention awareness. During the task, participants were asked to work on a puzzle game, and we interrupted them from time to time to let them report their partner's locus of attention as soon as they can. We compared a system condition with a video condition where they viewed a video streaming. The results shows that participants took more time to guess the partner's attention in the video condition than in our system condition. More interestingly, the analysis of head rotations showed a significant difference in their head rotations when guessing their partner's locus of attention. As you can see, in video condition, participants moved their head more to check on the monitor. In the system condition, on the other hand, they didn't even have to look at the robot because they had peripheral awareness that they were able to guess through their peripheral vision. Also, during our interview sessions, 10 out of 13 participants commented on peripheral awareness. These results show a promising feature of the RemoteCoDe, that is the affordance of peripheral awareness. This implies that they can focus on a design task around a physical artifact while being able to perceive what other collaborators are doing. In summary, we present the design of RemoteCoDe, an automatic robotic embodiment for design activities. We demonstrate the remapping technique that accommodates different configurations in each location. Finally, we reported on the evaluation that RemoteCoDe affords peripheral awareness during a hands-on task. Finally, I'd like to thank all the collaborators for this work, including my advisor at Cornell, Francois Gembatia, and 2 other PhD students, Andy Rich and Jaitin Aurora. This work was supported by NSF and Nakajima Foundation. Thank you so much for listening.